Assalamualaikum Doctor. My name is AMIRA SHAFIQAH. So my bachelor project entitled Physical and Bioactivity Properties of Bioactive Glass for Bone Scaffolding. So as an introduction, issues related to traditional bone repair and regeneration therapies have contributed to the needs for new technologies for advanced bone regeneration such as a bone scaffold. Bone scaffolds are materials that provide mechanical and functional support during bone regeneration. So bioactive glass is one of the most common synthetic material used in a bone scaffold. Good porosity bioactive glass should have high porosity to enable cell penetration, oxygen, and nutrient exchange to support the functionality of bone tissues are desired. So the aim of the study is to investigate the feasibility of using binders to create a functional bioactivity glass for 3D bone scaffold. So this research have three objectives. First is to evaluate the effect of drying time on the binding efficiency of a sago starch and xanthan gum. The second one is to evaluate the ability of hydroxyapatite formation on its surface in the simulated body fluid. And the third one is to assess the suitable bioactivity and degradation model of a bioactive glass. But then the study have a limit, such as the synthesis method of a bioactive glass is limited to only salt gel method, although there are many other methods to synthesize bioactive glass due to time constraint. The second one is the SPF difficult to determine what effect the presence of plasma protein may have on HA condensation, ion absorption on a scaffold surface. So this is the research framework for this project. We have three objectives. For the first one, we synthesize the bioactive glass via salt gel method. We use CNF10 as a template. We use different binders such as a sago starch and xanthan gum. We place into the mold, we dry it, and we test it using load test and a mechanical test. For the second objective, to evaluate the hydroxyapatite formation, we put the tablet in the SPF, we dry it in the desiccator, and we analyze it using SEM and XRD. And for the third objective, to assess the suitable bioactivity and degradation model, we choose the solution model. So for the first objective, to evaluate the effect of drying time on the binding efficiency of a sago starch and xanthan gum. Based on the image presented here, it can be observed that after day 1, the DG tablet prepared using both sago starch and xanthan gum was still wet and strongly attached to the mold. So if the sample is removed, then there is a high possibility that the tablets are cracked and crushed because the loose powder are not properly bound yet. For example, for a tablet collected after day 3, it can be noticed that there are still some left over, about 50% attached to the mold for BG tablet prepared using both binder. BG tablet bound using xanthan gum seem to be much drier and thus have less mass attached to the mold. This indicates that the xanthan gum dried much faster compared to the sago starch. For the sago starch, it completely dried for 7 days, but for the xanthan, it's only take 5 days. So this is the perfect structure of the tablet and being used for the second objective. We also done the strength analysis using Instron 3365 in the mechanical lab. So this specimen is 10 times 5 mm. We dry it for 7 days. So this is the collapse structure when the maximum load is applied. So this is the graph of compressive load versus compressive extension for Sagostage as a binder. So based on this table, the mean maximum load for the BG after being calculated is 30.5 Newton with a compressive strength value of 1.56 MPa. We ignore these first two, and we just only consider the three. So this is for the xanthan gum. It shows that the tablet cannot sustain even when the load is applied. So as a conclusion, by comparing these two graphs, it shows that when using Sagostage as a binder, the tablet can sustain longer over a range of compressive strings before it fails. The tablet prepared using xanthan gum is strong but fails abruptly. So for the second objective is to evaluate the ability of hydroxyapatite formation on its surface in the simulated body fluid. We test the commercial hydroxyapatite using XRD. So this is the graph. The two theta values of hydroxyapatite is a range about 20 to 70. The peak octane of this XRD is 26, 32, and 46.6 degree. So this shows that hydroxyapatite formations so that we can compare the XRD of HA with the one that we done with our tablet. So this is the SEM image for the Sagostage as a binder. Based on this figure, it shows that the BG is formed by a long tubular structure before it immerses in the SPF. The average diameter of the measured bioactive class was quite uniform and appeared to have high aspect ratio. This indicates that the fiber is in a nano size and within the size range suitable to create internal connectivity of bond scaffold. So, but then after it immersed for 7 days, it can be inferred that majority of the particles were bonded together. There are various grains of uniform shape and size on the surface of the samples. It's clearly observed there are hydroxyapatite layers are formed. For the figure C, it shows from the 7 days, the thickness of hydroxyapatite increased after 21 days immersed in the SBF. So this is the XRD analysis to make sure to know the crystallinity of the sample. So if we can see here, when the time increase, the crystallinity also increase. For the xanthan gum, based on their figure, it can be observed that the crystal formation appears on the surface of the tablet when it immerses for 7 and 21 days. Based on this figure, it can be observed that first there is no apatite layer formed, but after 7 days, it shows the surface appears as a hexagonal structure, there is a possibility that the AMIRA section of the bioactive class were removed as a result of formations of hydroxyapatite after immerse in SBF for these 7 days. After 21 days, this picture shows that the surface have more crack and the characteristic of hydroxyapatites if observed. So for the XRD analysis, it clearly perceives here that after 21 days, the peak is higher compared to the 7 days. So when the time increase, the hydroxyapatite formations also increase. The third objective is to assess the suitable bioactivity and degradation model of bioactive class. We have pH variation here for sago starch and xanthan gum. Noted that the first stage of bioactivity gives rise to a depletion of the hydrogen ions in the solution, thus producing a slight enhancement of pH. The pH estimation were made to know the dissolution behavior of the test in the SBF. So if we compare between the two, the dissolution behavior of xanthan gum is higher compared to sago starch. pH of the arrangement increment as a result of H plus particles within the arrangement being supplanted by cation. The pH of the arrangement increment due to the utilization of H plus particle. So this is the weight loss of this one. The left hand side is for xanthan and the right is for sago. We can see here there are no much difference between the two, between these two binders. So for the degradation versus timeless time, 4 different cases were analyzed to represent the bioactivity and biomaterial degradation of the 3D scaffold, namely case 1, case 2, case 3, and case 4 with different Kp and D. So this is the graph of the case study. Based on these figures, the effect of diffusion and precipitation velocity parameters can be understood in these models. It indicates that the quick precipitation velocity results in the formation of hydroxyapatite layer even when the diffusion is low. The slow dissolution rate slows down the precipitation phenomena because the surrounding SPF does not obtain any release ion. So if we can see here, the degradation increase within the time, even for the 4 cases. As a conclusion, a very fast degradation rate combined with a slow rate of precipitation result in the biomaterials complete disappears before the immersion period ends. So as a conclusion, the optimum drying time for the binder using sago starch was 7 days and xanthan gum was 5 days. The variation of pH shows the formation of apatite layer. pH increased within the time. XRD results demonstrate that the bioactivity glass tablets by using xanthan gum as a binder has good bioactivity in vitro, and their mineralization product was hydroxyapatite. Because we can see before this, the peak is high compared to the others. So this research shows that the potential of using food materials as good biocompatible binders for 3D scaffold. So for the recommendation, future research should focus on the varying amount of binder to be used and the modeling of the biodegradation and dissolution. I think that's all. Thank you.